Bismillahirrahmanirrahim. Assalamu alaikum, dear students. We are now starting the lectures for ninth week for wireless and mobile communications. This is our first lecture for this week. In this lecture, we are starting a new topic which is related to modulation techniques for mobile radios. We already know that modulation is one of the important operations for any communication systems. For today's lecture, in fact for this week's lecture, we will be discussing different modulation techniques which are used for mobile radios. We know that generally we work on two different types of communication systems. Either the communication systems that we are considering is an analog communication system or a digital communication systems. So current trend is actually the digital communication systems. The modulation techniques which are used in communication systems is related to the type of communication systems which are being used. We either use analog type of modulation or digital type of modulation scheme. So the question is, what is modulation? Modulation is actually the process of imposing low frequency information onto a high frequency carrier for transmission. Generally the transmission from a channel requires having a higher frequency, but the information signals, they are typically at lower frequencies. Take for example audio signals. Audio signals, they are at low frequency when they are generated. For example, when we talk, our microphone transforms a signal into electrical form. That signal generally contains the frequencies up to 4 kilohertz, which is a low frequency signal. We call that signal as a baseband signal. This information signal, which is the baseband or low frequency signal, when it is sent over a wireless channel or mobile radio channel, it cannot be transmitted through mobile radio channel without any type of modulation because of the filtering effect of a wireless channel. Generally, the wireless channel, it allows propagation of relatively higher frequencies, and the low frequency signal, they do not propagate to a longer distances. So in order to transmit this low frequency baseband signal from a mobile radio channel, we need to have a frequency translation. We need to shift the frequency of this baseband signal to a relatively higher frequencies, which becomes a band pass signal. So we have to transform this low pass signal into a band pass signal which occupies a relatively higher frequencies. In order to do that, we generally take a high frequency carrier, which is generally a sinusoidal signal. So we modulate that carrier, high frequency sinusoidal carrier, by using the information signal, so that then the overall signal becomes a high frequency modulated signal which contains the modulated carrier or which contains the frequency shifted version of the original baseband signal. This is generally called a band pass signal. So in the process of modulation, we employ a high frequency sinusoidal carrier to shift the frequencies of the baseband information signal to take it to a relatively higher frequencies. Different characteristics of carrier can be changed when we modulate the signal. These characteristics can be amplitude, frequency, phase, or maybe in some cases the combination of these two. So for analog communication systems, we use an analog modulator and transmits the signal over a transmission channel. The analog modulator is actually transforms the baseband signal into an analog band pass signal, or in other words, it translates the frequency and shifts the signal towards the higher frequencies by using a high frequency sinusoidal carrier. So output will be a modulated signal. The typical examples can be AM and FM signals. When the signal is received at the receiver side, we use a demodulator, analog demodulator, which reconstructs or recover the baseband signal from that received signal. In other words, this demodulator removes the high frequency carrier so that the signal is recovered to its original form of a baseband signal. So this demodulated signal transforms this analog bandpass signal into an analog baseband signal. So output will be the original analog baseband signal, which is in the original form as of source. In digital communication systems, we can have a lot more operations as compared to the analog communication. Generally, we have a source which can generate analog signal or digital signal. The source can have a signal in any form. We use a source encoder to transform that original signal into a binary bits or into a digital signal. The output of the source encoder would be bits or a digital signal that represents the original information. Then we use a channel encoder. Channel encoder actually is used for controlling the error during transmission. From having channel encoder, we can either detect, or in some cases we can also correct the errors which occur during transmission because of the presence of noise and adverse effect by other channel phenomena. The channel encoder actually adds some redundant bits with a certain rule so that those redundant bits, they are used to check whether there is an error during transmission or not, and using those redundant bits, in some cases we are able to correct those errors. The output of channel encoder would be a digital code word which makes a block of bits to represent a channel code word. Then we use a digital modulator. Digital modulator actually maps that digital symbols into an analog baseband waveform, which is using a sinusoidal signal. This analog bandpass waveform is actually using a sinusoidal carrier, but it represents the digital information which is represented by which is used to represent the code word information which is received from the channel encoder. So digital modulator generates sinusoidal waveforms in order to transmit it over a transmission channel. At the receiver side, this process is reversed. The bottom blocks, they are representing the receiver sides. The digital demodulator, it actually removes that sinusoidal signal and detects the original words which are being transmitted. Those words are then delivered to the channel decoder, which checks them for any error and then removes those redundant bits. The received bit binary data is delivered to the source decoder, which transforms the signal into the original format so that the information is delivered to the sink. So this is an overall flow of digital communication systems. Let us start discussion on different types of modulation schemes that we use for analog and digital communication systems. So we begin our discussion with analog modulation. As I mentioned that we use a sinusoidal carrier for modulation purposes. So this is the generalized form of a sinusoidal carrier. A carrier can have a specific amplitude. There would be certain frequency related to that carrier, and there may be some phase related to that carrier. So this is the representation of that sinusoidal carrier, which is described by three different pieces of information containing amplitude, frequency, and phase. When we modulate any signal, whenever we employ this carrier for modulation purposes, so we apply a modulating signal. So say for example we have a modulating signal which is represented here, and here we are taking two examples of modulating signal. So this modulating signal changes one of the properties of the sinusoidal carrier. Either it changes amplitude, which is named as amplitude modulation, or it changes the frequency of the carrier, which is named as frequency modulation, or it changes the phase of the sinusoidal carrier, which is named as phase modulation. So there are three different possibilities of analog modulation. Either we change amplitude or frequency or phase of the sinusoidal carrier to represent the information of baseband signal. So say for example we are using an amplitude modulation. So you can see that this amplitude of the sinusoidal carrier is changing with relevant to the modulating signal. So as the amplitude of modulating signal increases, the amplitude of this sinusoidal carrier also increases to represent the information in the modulating signal. Similarly, you can see here the amplitude or envelope of this waveform follows the modulating signal. So amplitude is actually changing with respect to the modulating signal. In frequency modulation, the frequency of the waveform changes with respect to the modulating signal. So you can see that the point where the amplitude is relatively higher for modulating signal, we see a relatively high frequency of the waveform here. Similarly, in this example of sinusoidal function, we have these points represents the high amplitudes of modulating signal, and the corresponding frequencies of the sinusoidal carriers are higher, and this point is representing the low amplitude of the modulating signal. So the corresponding point in the sinusoidal carrier contains relatively lower frequency. Similarly, for phase modulation, the phase of the modulating signal increases as the amplitude of the modulating phase of the sinusoidal carrier increases as the amplitude of modulating signal increases. So the point where we have higher amplitude, you can see that the phase is shifting towards a higher value. So phase is basically shifting here. Similarly here for this example, at the higher values you have some phase, but as the values goes towards a lower value, the phase starts shifting towards relatively lower value. So we see a shift in the phase of the modulating of the sinusoidal carrier as we change the amplitude of the modulating signal. So these three types of modulations are used are commonly used in different mobile radios. Generally, as I mentioned, that the early days, the initial generations of mobile radios were based on the analog modulation. We have used AM and FM modulation, and now FM modulation is also used for generally for radio broadcasting as well. We have FM radios available which also use this FM modulation. So just for a comparison purposes, we make a comparison between amplitude modulation, that is AM, and FM. AM modulation is relatively cheaper as the transmitter and receiver are relatively simple, but on the contrary, the frequency modulation, the receiver and transmitter circuitry, they are relatively complex because we need to change the frequencies in comparison to the corresponding changes in the amplitude of the modulating signal. For AM signals, whenever we use single sideband or whenever we use a modulation scheme where we have suppressed the carrier, in that case we need to have a good synchronization among the systems so that we can detect the information. So there is a need of synchronization as well for some types of AM modulations. Typical ranges for AM modulated waves which are used practically are from 535 kHz to 1715 kHz, and they can support a data rate of up to 1200 bits per second. FM radios, they support broadcast at relatively higher spectrum, which is used for 88 to 108 megahertz, and they typically support data rate from 1200 to 2400 bits per second. So you can see that the FM modulation works at relatively higher frequency band with a higher data rate. AM modulation has a poor sound quality, whereas the FM modulated signal contains a relatively better sound quality because of the immunity to noise. The AM signal can transmit longer as compared to the FM signal. The FM signal have a shorter coverage as compared to AM. You can see from this point as well. We know that the AM modulation is used for relatively lower frequencies, and we know that from our path loss modeling and analysis that the path loss during propagation is also dependent on the frequency. So the signals which are having at lower frequency, they generally have relatively smaller path loss, and in that case the coverage area is relatively large. But the signals which are at relatively higher frequencies as FM modulation, they have associated a relatively large path loss, and eventually the coverage area would be small. AM signals, they require lower bandwidth as compared to the FM signals. Generally in AM signals there are only two sidebands, an upper sideband and lower sideband. So overall transmission bandwidth required is double of that of the modulating signal. But for FM signals, depending on the modulation index, we generally need more than two sidebands. So eventually the FM requires a larger bandwidth. AM is more susceptible to noise because noise generally affects the amplitude, and for AM signal the information is stored in the amplitude of the AM signal, and as the noise changes the amplitude, eventually it changes the information contents and causes error in the transmission. FM signal is less susceptible to noise because the variations in amplitude does not cause the variation in the frequency. So because our information is stored as variation in the frequency, so we do not see effect of noise significantly. Secondly, FM is also less prone to interference. The interference effect is negligible in FM as compared to AM because of the capture effect. Okay, let us take some examples, considering that we have a basic understanding of AM and FM signal from our communication systems course. So we take a few examples and then we will move on to the digital modulation schemes. So say for example we have a zero mean sinusoidal message is applied to a transmitter that radiates an AM signal with a power of 10 kilowatt. So power in a transmitted AM signal is represented as 10 kilowatt. The carrier, we want to compute the carrier power if the modulation index is 0.6. So we know the modulation index, which is defined as the amplitude of modulating signal divided by amplitude of the carrier wave. This is 0.6. So we want to find the carrier power, and also we want to calculate the power in each of the side bands, and also it is requested that if the modulating signal is 4 kilohertz audio wave, what will be the bandwidth of AM signal. So let us start our calculation. For AM signal, actually the power is in three parts. There are three different components of the power. First one is the power in the carrier, because there is a carrier which is transmitted in AM signals. Second, there is a sideband which is named as lower sideband, and third is an upper sideband. So we have two sidebands and the carrier in AM signal. So the power is divided among carrier and the sidebands depending on the modulation index m. The power in each of the sideband, lower sideband or upper sideband, is represented by this relationship m square Pc over 4, where Pc is the carrier power and m square is the modulation index. So if I substitute this value here, so I would see that the power in AM signal can be represented as Pc plus m square Pc by 4 plus m square Pc by 4. And you can see that in these terms Pc is common, so I can take this Pc as common. The value of m is known as 0.6, or if I substitute it, I will get 0.36. Square of 0.6 is 0.36. And PAM, the power in AM signal is given as 10 kilowatt, so 10 into 10 raised to power 3. Therefore the carrier power would be given as this fraction 10 into 10 raised to power 3 divided by 1.18, which comes out to be 8.47 into 10 raised to power 3 watt. So this is the power in the carrier. Actually in question we were asked to calculate the percentage of power in the carrier. So we transform this 8.47 into 10 raised to power 3 into percentage. So in order to transform it percentage, we divide it with the total power, which is power in the AM signal, and multiply it by 100. So we get that there is 84.7% power which will be in the carrier. Also we need to calculate the power in each of the side bands. We can calculate the power in each of the side bands by this relationship m square Pc by 4. Now we know Pc which is 8.47 into 10 raised to power 3. So if I substitute these values, so we would see that the power in each of the sideband comes out to be 0.765 kilowatt. Okay. The last thing which is asked in the question is the bandwidth of the AM signal. The bandwidth of the signal is actually, AM signal is double that of the modulating signal, and the modulating signal bandwidth was given in question as 4 kilohertz. So we can say that the bandwidth of AM signal would be 8 kilohertz for this particular case. Okay. Let us take another problem related to FM modulation. Say for example we have a sinusoidal modulating signal which is represented here. Mt is equal to 4 cos 2 pi into 4 into 10 raised to power 3 t. So you can see that is this part 4 into 10 raised to power 3 is actually representing the frequency of modulating signal. So FM frequency is given as 4 kilohertz here. The amplitude is given as 4. As we know that the FM signals they have certain frequency deviation, because as the amplitude of the modulating signal changes, we see some change in the frequency of of the carrier. So that frequency deviation is represented by frequency deviation constant gain of 10 kilohertz per volt. So frequency deviation constant is 10 kilohertz per volt, which is given. So for 1 volt change in the amplitude of the modulating signal, we would see a frequency change of 10 kilohertz in the modulated signal. So what is the peak frequency deviation? You can see that the peak frequency deviation would be related to the peak modulating signal amplitude, which is given as 4 here. So the peak frequency deviation is actually 4 volt multiplied by this frequency deviation constant 10 kilohertz. So the maximum frequency deviation that we will observe in our modulated signal would be 40 kilohertz. So maximum deviation would be 40 kilohertz only in the modulated signal. Second thing which is asked is the modulation index. For FM modulation, the modulation index is defined as the ratio of this maximum frequency deviation to the frequency of the modulating signal. So the maximum frequency deviation is 40 kilohertz, whereas the modulating signal frequency is given as 4 kilohertz. So if we divide those two, we see that the modulation index for this FM signal comes out to be 10. As I mentioned, the bandwidth. The third thing which was asked for was what is the bandwidth of the FM signal. I mentioned before that depending on the modulation index, the bandwidth, there are a number of side bands which are important in FM signals. So FM bandwidth is relatively large as compared to the AM signals, and this depends on how many side bands are significant for transmission. So in order to calculate bandwidths, there are certain tables available, but there is a mathematical rule which can also be used to estimate the bandwidth of an FM signal. So this rule is named as Carson's rule. Carson's rule gives you an approximation on the bandwidth of FM signal, and this rule defines the bandwidth as a function of modulating signal, frequency of modulating signal, and modulation index. So bandwidth of FM signal is represented as twice of this beta plus 1, which is the beta is the modulation index multiplied by FM. So if I substitute the value, we know that beta is 10 here, and frequency of modulating signal is 4 kilohertz. So if I substitute it here and simplify, we would see that the bandwidth would be 88 kilohertz. You can compare this bandwidth with the previous case of AM signal. In that case, we also had the modulating signal of 4 kilohertz, but the required bandwidth for transmission was 8 kilohertz. But for the case of FM signals, we have the modulating signal of 4 kilohertz, but the required bandwidth for transmission is 88 kilohertz. So FM requires relatively larger bandwidth, but this larger bandwidth gives a benefit of noise reduction. Generally FM signals, they are very good at reducing the effect of noise. So this larger bandwidth would translate into a better signal to noise ratio when we see the quality of signal at the receiver side. So this was a discussion related to the analog transmission. So now let us move on to the digital modulation. The modern communication systems, they typically using digital modulations because of the variety of advantages that we get from the digital modulation. The digital modulation schemes, they have certain advantages as compared to the analog modulation methods, that is AM and FM. They are better in terms of the performance, and in general they are more cost effective, as we know that the digital hardware is generally low cost and more reliable as compared to the uh, analog hardwares. These digital modulation schemes are now commonly used in modern cellular systems. One of the biggest advantages that we get in digital schemes is that we have possibility of regenerating the digital signals. So we can use regenerative repeaters to recover the original information at periodic intervals. So this regenerative repeaters, they prevent the accumulation of noise and interference during digital transmission. So this is one of the biggest advantages that we get from the digital modulation. Also, we have seen a significant advancement in different related technologies, including VLSI and digital signal processing methods, and they have become more practical and affordable from cost and reliability point of view. So with using these methods, we have got the advantages of having digital signal processing at a very low cost. Secondly, for different multiplexing schemes are also available for digital modulation. For analog modulation, the most commonly used multiplexing scheme is frequency division multiplexing. Normally, we only rely on the frequency division, but for digital schemes, we have other schemes as well. For example, time division multiplexing and code division multiplexing, which can give better performance in certain scenarios. So from digital modulation, we get variety of different advantages. In order to give an insight, we have listed a few advantages that we get from using digital modulation. First of all, this is the digital modulation are resistance to noise, fading and interference effect. So effect of these phenomena is significantly less in digital systems as compared to the analog systems. In digital communications, different types of information can be combined into a single transmission channel. We do not need to incorporate different transmission channels for different types of information. So we can transmit voice, data, or video onto a same channel, because when we digitize the information, all the information can be represented by bits. So a bit is a bit. It does not matter whether it's coming from a video or a voice or any other type of information. So once it's represented in form of bits, you can transmit all the bits onto the same channel. So all different types of information can be transmitted from the same channel. In digital systems, we have relatively improved security because we have different encryption algorithms which can be implemented on digital systems easily. So this also these security features in digital information, they represent a better performance in terms of the information security, so that your information does not go to any unwanted recipient. So or any unwanted recipient cannot access your information. For digital system, we have potential of using error control coding. So we can have a coding scheme which can be employed in order to detect or correct transmission errors which occur during transmission for different types of environment. So we can have coding using those coding schemes. We can get the better performance by using some error control algorithms. Signal conditioning is available in digital systems because the mobile radio communication channel environment is relatively hostile. So using that signal conditioning, we can prevent our signal information when it passes through that hostile mobile radio channel. In digital systems, the modulation and demodulation function can be incorporated in the DSP software instead of having a separate hardware. So in implementing this modulation and demodulation function on the DSP softwares gives you relatively high flexibility as compared to the analog signals, so that if you want to make any change in the system, we just need to change the software and we do not need to go for any replacement in the hardware circuitry. For digital modulation, there are variety of different modulation schemes which are available and which are in use for different types of environment. So why do we have so many different digital modulation schemes? Actually, these schemes are based on the variety of performance factors which we consider when we plan for any digital modulation scheme. So if you are planning a system and you need to decide which type of modulation scheme you want to use, so we generally refer to different performance criteria and choose the modulation scheme which best gives that performance criteria. So these performance criteria include low bit error rate. We want to have a relatively low error when the signal transmits at the channel, and we also want to have this low bit error BER at low signal to noise ratio. So because having low signal to noise ratio means we want to put in lesser amount of power to the signal, and with that lesser amount of power we want to have as low bit error rate as possible. We also want to have our modulation scheme to be resistant to interferences. Different types of interferences occur during transmission as adjacent channel interference and common co-channel interference we have discussed in detail previously. So we want to have the modulation scheme which does not get affected by the interference. Also, we want to have the minimum effect of multipath fading. So we would prefer a modulation scheme which does not degrade the performance even if there is a multipath fading in the environment. Third important criteria is occupancy of the bandwidth. We want to have minimum possible bandwidth and transmit the signal using the minimum possible bandwidth. Fourth is the implementation point of view. We want to have easy and cheap implementation on the mobile equipment. So whatever modulation scheme we want to use, that should be implementable on a mobile equipment easily, as well as it should not cost high, so that the equipment cost remains in the reasonable level. We also want to have efficient use of battery power for the mobile units, because mobile units they have limited amount of batteries, so we want to have as efficient battery use as possible. Unfortunately, these requirements they are contrary to each other, and we do not have any specific modulation schemes which simultaneously satisfies all these requirements. So we generally make a trade-off between these requirements, and we come up with a specific modulation scheme. So if any certain environment the battery power is critical, so we would go for the modulation scheme which is better in the battery power performance, although it may have lower relatively higher bit error rate, or maybe it may have relatively higher bandwidth, or vice versa. So we need to have a trade-off when we decide which type of modulation scheme we should use for any type of environment. So with this we had a basic introduction on the digital modulation schemes. We will continue this topic in our subsequent lectures for this week, inshallah. and we would also discuss different types of digital modulation schemes that are being used for mobile radio channels. So we stop our discussion here. Inshallah, we'll continue in next lecture. Thank you.